Okay, now this next section. This is Math 2412, Monday, date 10, 2/19/24. Chapter 4, Section 3. The properties of rational functions. Again, rational means fractions. So, for example, we would have f of x equals x squared minus 4, x squared plus x plus 1. G of x is x squared minus 4, and h of x is going to be 3x cubed over x to the 4th minus 1, or 3x squared. These are all rational expressions. By definition, a rational function is a function of the form r of x equals p of x over q of x. Where p and q are polynomial functions. And q of x does not equal 0. Okay, so the first objective of this section is how to find the domain of a rational function. Remember, domain is the x values. So let's look at an example. Two x squared minus 4, x plus 5. The rule is you cannot have a 0 on the bottom. So set the denominator equal to 0 and solve. So we have x plus 5 equals 0, x equals negative 5. We can use all x's except negative 5. So x cannot equal negative 5. Another example. 1 over x squared minus 4. Again, there's two ways you do this. One, you could take the bottom, set it equal to 0. And when you square root it, x equals plus or minus 2. So our restriction is we can use all x's except plus or minus 2. We could have also factored it out. This is a difference of two squares. Which is x plus 2, x minus 2. So x cannot equal negative 2 or positive 2. X squared plus 1. Because this is a plus, and this is an even exponent, there are no restrictions on x. It could be any values it wants to. So x squared minus 1, x minus 1. Before we do anything, we look at the bottom. So x cannot equal 1. That's my restriction. But it's got a special name. Because if we look at the top, we have the difference of two squares. Remember, a difference of two squares is a plus b, a minus b. You notice how these can cancel, leaving us with x plus 1. We still cannot use 1 as an answer. This is called a removable discontinuity. Removable discontinuity, because, I mean, we can remove it, but we still can't use it. It's just, now we have a simpler equation to deal with. All right. Let's look at example 2. One over x squared. This one says that x cannot equal 0. Since we know we cannot use 0, so look at what happens on both sides. When x is 1, y is 1. When x is 2, it's 1/4. So it's going to come down here. When x is 3, it's 1/9 and 1/16. But when we go, let's say 1/2, 1 over 1/2 squared, which is 1 over 1 over 4. Take the top, leave it alone, flip the bottom. So our graph looks like this. On the positive side, we can't use 0. That's an asymptote. But on the negative side, negative in there, we square it, becomes positive. It'll look the same. It'll look like the Atari symbol. We plot some points and we see what's going on. So this is just a reciprocal function. Is the bigger the bottom gets, the smaller the entire equation gets. All right, let's look at the next one. We can use transformations in our functions. So we know that one, the basic function this is 1 over x squared. So we know what it looks like. The next thing that happens to it is what happens inside the function. Remember, when x is 0, the origin is there. What did I do here? So let's take that denominator, set it equal to 0. That means it shifted to the right 2 spaces. This is my new y-axis. I shifted it from here to there. So the graph still looks the same, but just shifted to the right. So we know what this does. Now the whole thing goes up 1. So we shifted over 2 to the, now we shift up 1. So my new origin is right there. I shifted it over 2, up 1. So my graph looks like this now. Again, you could plot points and figure that out slowly. So whenever you have rational equations, you look for things called asymptotes. An asymptote is an imaginary line that the graph cannot cross. We have 2 types of asymptotes. We have a vertical asymptote and we have a horizontal. So this one, the vertical asymptote, the graph never crosses a vertical asymptote because vertical asymptotes are created whenever the denominator equals 0. But it is possible that the graph may intersect or cross a horizontal asymptote, but it will taper back down to that asymptote. So let's look at the verticals. Where the denominator equals 0. Remember, you cannot have a 0 on the bottom. So if I have this equation, the vertical asymptote, take the bottom, set it equal to 0, and that's your vertical asymptote, because x cannot equal -1. So that's your vertical asymptote. How about this one? The vertical asymptote, set the bottom equal to 0, square root both sides. So x equals plus or minus 2. So those are my vertical asymptotes. X squared plus 1. The vertical asymptote, take the bottom, set it equal to 0. That has no vertical asymptote because the bottom can never equal 0. And let's look at this one. So the vertical asymptote, x squared plus 4x minus 20 equals 0. X. This is opposite signs. One's positive, one's negative. The bigger one's positive. What times what is 21? When you subtract them, you get 7, or you get 4. 7 times 3, 7 minus 3. So x equals -7 and x equals 3. Those are my vertical asymptotes. Now, but this is not complete because we have a factored form. We know the bottom is x plus 7 and the top x minus 3, and the top, the difference of two squares. It's x plus 3, x minus 3. So the x minus 3 is a removable discontinuity. So at x equals 3, there is a hole. It is a removable discontinuity. So The only vertical asymptote we have is at x equals -7. Now let's get multiplicities and the vertical asymptote. So, for example, we had something like this. Yeah, this is a horizontal shift to the right one. All right, two, I mean. So the graph looks like this. The multiplicity is 1. So is it odd or even? It's odd. So since the multiplicity is odd, they point as x approaches 2 from the left, the function approaches -infinity. As x approaches 2 from the right, the function approaches +infinity. So the next one, f of x equals -1/x minus 2. This is similar to that one, except it has negative. So it's shifted over 2, but the graph is flipped because it's outside of it. So the multiplicity is still odd. It's 1. As x approaches 2 from the left, the function goes to +infinity. As x approaches 2 from the right, the function goes to -infinity. Now we have an even multiplicity. Multiplicity is 2. It shifts to the right 2. And it's positive. I mean, it's squared, so it's never negative. As x approaches 2 from the left, the function goes to +infinity. As x approaches 2 from the right, the function also goes to +infinity. And the last one, -1/x minus 2 squared. We know the multiplicity is even, it's 2. It shifts to the right 2 spaces, but it now goes down because the entire function is outside the function, so it flips across the x-axis. As x approaches 2 from the left, f of x approaches negative infinity. As x approaches 2 from the right. So what you see here with odd multiplicities, we see that the function approaches two separate directions. If it's even, they approach the same direction, same value. So if it's even, they both approach the same solution. All right, now let's look at horizontal asymptotes. Or oblique asymptotes. Now, horizontal asymptotes are, you can only have one. You can have multiple x vertical asymptotes, but you can only have one horizontal or oblique. If it's, you can only have one or the other. You cannot have both in an equation. So in any rational equation, you only have to look at the leading terms. So you only look at the leading terms. More so, their degrees. The degrees are m and n. The horizontal asymptote is zero if m is bigger than n. Or just saying here is, if I had x to the third and x to the fifth, again, the rest of the equation is zero because this one dictates most of the function. If I simplify those, I have 3 there, I have 5 there, so I take away 3. Now, as x gets bigger, as x goes to infinity, this number goes to 0. So the horizontal asymptote is 0, meaning the horizontal asymptote is the x-axis. If the bottom is bigger than the top. The horizontal asymptote is undefined if the top is bigger than the bottom. And as x goes to infinity, this value goes to infinity. So it's undefined. There is no horizontal asymptote. If the degrees are the same, then the horizontal asymptote is simply the coefficients. 2x to the third, 3x to the third. The x to the thirds cancel, so we have 2/3. And that's your horizontal asymptote. All right, so let's look at some of these, and then we'll talk about obliques. There's always an exception to the rule. Some good ones here. 4x to the third minus 3x plus 2, 7x to the third, 2x, no, let's make it fifth, x to the fourth minus 3x. The horizontal asymptote. So n is equal to 3, m is equal to 5. So we have 1 over x squared, which goes to 0. So the horizontal asymptote is 0. Yeah, forget about the rest of the stuff. Since the x's, the degrees are the same, the horizontal asymptote is simply the coefficient. The top n is 5, m is 3, so it goes to infinity, so does not exist. There's no horizontal asymptote. Except if n is 1 bigger than m. Top degree is 1 larger than the bottom. Then you have an oblique or slant asymptote. So x squared plus 3x 2 Since n is 2, m is 1, n is bigger than m, but n is equal to m plus 1. So we have an oblique asymptote. To find the oblique asymptote, do long division. And drop any remainder. So we have x squared plus 3x plus 2, x plus 1. So x times what gives me x squared? X. X times x is x squared. X times 1 is x. Change the signs and add. 3 minus 1 is 2x. Bring down. What times x gives me 2x? Positive 2. 2 times x is 2x. 2 times 1 is 2. Change the signs. This is my oblique. Nerds, the oblique asymptote would be like this. All right, so here's an example. We see that we have here, we have the top n equals 4, m equals 3. Since n equals m plus 1, we have an oblique asymptote. So, in order to find it, we take the bottom and do long division. All zeros in there needed. So, what times x cubed gives me 3x to the 4th? 3 times 1 is 3. I need one more x. So 3x times x cubed is 3x to the 4th. 3x times negative x squared is negative 3x cubed. Oh, one more. Times 3x. Times 1. Change the signs and add. So that cancels. So this becomes 3x cubed minus x squared minus 3x plus 0. What times x cubed gives me 3x cubed? So 3 times x cubed is 3x cubed. 3 times negative, so it's negative 3x squared. 3 times 1 is 3. Change the signs. That cancels. 3 minus 1 is 2x squared. But this is all remainder because it's smaller than that. Oblique asymptotes always linear equations, because it's always, since it's one less than the top, it'll always cancel out. All right. Let me look for another example here. All right, find oblique. Find the horizontal asymptote or oblique asymptote. Eight x squared minus x plus 2, 4x squared minus 1. N equals 2, m equals 2, they cancel. So it's just the coefficients. It's a horizontal asymptote. So the horizontal asymptote is at 2. Example 8. Two x to the 5th minus x cubed plus 2. So we have n equals 5, m equals 3, which leaves 2 more on top. So there's no horizontal asymptote. Do we have a vertical asymptote? So we set the bottom equal to 0. So vertical asymptote, x cubed minus 1 equals 0. X cubed equals 1. So x equals cube root of 1, which is 1. So the vertical asymptote is at 1. So we have vertical asymptote here. The line cannot cross that. We have no horizontal asymptote. All right, let's see what we do here. Do we have any x-intercepts? Since it's cubic, Let's see, I'm going to plug in some points. Uh-oh, when okay, when x equals negative one, x is 0. We have 2 over negative 1, so it's negative 2. When x is negative 1, so we have negative 2 plus 1 plus 2. Negative 1 minus 1 is 1 over negative 2. Negative 1/2. When x is negative 2, 2, 4, 8, 32, so it's negative 64 plus 8 plus 2 is negative 54 over negative 9. Would be positive. 9 goes in 5, 6 times. Equals 6. So the graph will look something like this. It's always decreasing function. And on this side, when x is 2, we got 64 minus 8 plus 2, 58 over 7. You get over 7. 7 times 7 is 49, so 7 point something. I can't use 1. So when I subtract divide of these, then I get a squared term. So here I'm looking at a polynomial of degree 2, and the smallest it can go is around 1.5. So it looks something like that. Yeah, but if we look at these guys here, it'll become 2x squared because x cubed and x fifth cancel out. Again, you can use any type of tool you want to graph those for you. Okay, let's see here. I think that's about it. A polynomial of horizontal, vertical, and oblique asymptotes. All right, we'll pick up from here next time on section 4. Everybody, have a great day. Any questions? All right, have a great day. You okay?
Yeah, I was just waiting. How are you doing today?
Still a bit. My throat is killing me, and I'm still coughing and sneezing a bunch. I'm pounding myself with medication. So that's why I don't get anybody sick today.
Oh, okay, I understand.
So yeah, thank you very much. So I will see everybody I'll be better on Wednesday, I hope. So have a
Okay,
great day.
see you Wednesday.
Yes, sir.
You too. Thanks.